We're going to start the second part talking about wave behavior. And these are some special things that waves do that is somewhat unique to waves and is different from things that you would expect in other aspects of physics. In order to study this, we have to look at what's called a ripple tank. And a ripple tank is a device that's used to demonstrate different kinds of wave behavior. And the kinds of wave behavior we're going to be talking about are diffraction, reflection, refraction, and interference. And so I just want to give you a preview that we'll be talking about those specific wave behaviors, and the ripple tank has been used extensively to look at this. And if you look here, you can see that you have an oscillator or a paddle that bounces up and down and generates a series of transverse waves that are traveling from the oscillator to the end of the tank. And it's a shallow tank of waters, and that's to allow light to pass through, and you can actually see the waves very clearly underneath the ripple tank. And this helps you sort of figure out exactly what's going on with these waves. What this ripple tank does is it sets up what's called a wavefront. And a wavefront is the boundary of each wave crest. So if you look at these dark lines, those represent the height of the crest of each wave, and when the light passes through, it cannot pass through that as well, and so it comes out as a darker line. And then the white light, or the white line, represents the trough of each wave. Now, when we talk about the ray, and we will be talking about incident rays and reflective rays or refracted rays, the ray is a line that's drawn perpendicular to the wavefront, and it represents the direction that the wavefront is traveling. And so when you hear me talking about an incident ray, I'm talking about the wave, the direction the wave is traveling, a line that represents the direction the wave is traveling. So let's first talk about reflection. Reflection is defined as the change of a wave course after it strikes a barrier it cannot pass through. The path of this reflection is composed of an incident wave and a reflected wave. And the diagram here shows a reflected ray, and this can represent a front of water waves traveling toward a surface. It can reflect a light ray. It can reflect a sound wave. It can represent just about anything that is a wave and will follow the laws of wave behavior. But what's an incident ray? An incident ray is the waves that come in that strike the obstacle before it's reflected. And so in the diagram here, this is the ray on the left that's coming in, is labeled incident, and the angle there is labeled theta I, which stands for angle of incidence. The reflected ray is the waves that come off the obstacle after they've been reflected. It's the line on the right, and it is labeled reflected ray. And theta R represents the angle of reflection, or the angle that comes off. The normal is the dashed line in the middle. The dashed line in the middle is perpendicular to the surface, and the normal is used to measure as the reference point to measure both the incident angle and the reflected angle. And so the law of reflection states that the angle of incidence, that is theta I, is equal to the angle of the reflected ray, which is theta R. Now the second wave behavior that we would talk about is refraction. And this is represented in this situation. And for the purposes of our discussion, we will start to talk in terms of starting from the top of the slide down toward the bottom of the slide, so that the incident ray is on top as labeled, and the refracted ray is on the bottom as labeled. So refraction is when the path of a wave is changed or bent. And the reason it bends is because the velocity of the wave changes when it passes from one medium to another. The speed of a wave changes if the medium changes. So for example, if you have a sound wave that's traveling in air, it has a certain velocity. If it enters water, then the velocity changes, and when the velocity changes, the ray will bend. The incident ray is the wave that is traveling in the initial or first medium where you start out, thus the name incident. The refracted ray is the ray that travels once the second medium has been entered. And so you see at the interface is where the change occurs. You start out, it's an incident ray up until the interface, and then it turns when it enters the second medium. Now you notice there's a normal here, and this normal is defined the same way. It's a perpendicular to the interface between the two media. And the angles, the angle of incident and the angle of refraction, are again measured from the reference point of the normal. So you have the incident ray compared to the normal. That angle is called the angle of incidence. And then you have the refracted ray and its relationship to the normal, and that's the angle of refraction. Now, as it turns out, the wave will always bend toward the medium or the normal that slows them down, or away from the normal if it speeds up. So in the picture shown here, if you start at the top, then what this means is that the incident ray is traveling faster than the refracted ray. Because when it slows down going into the second median, it bends toward the normal, so that the refracted angle is less than the incident angle. In this next slide, we have a situation where we can look at it from a different point of view. Let's say, for example, that we start out inside the glass. And so the incident ray is this ray right here, okay? So it goes inside the glass and then into air on the outside. Since it's going slower than here, you see that it bends away from the normal, and the incident is less than the refracted ray. And that's because it speeds up here. So if it starts in air, the incident is going faster than the refracted ray here, so it bends toward the normal here, and then it bends away from the normal when it goes back out and it picks up speed again. Here, the only thing they show here is that the angle of refraction is different between glass and water, and generally that means that the ray travels at a different speed in water compared to glass. So if the ray slows down, the angle of incident is greater than the angle of refraction. If the ray speeds up when it passes into the new medium, then the angle of incident is less than the angle of refraction. Now here's another type of behavior, and this is an interesting behavior that waves demonstrate. Other types of materials do not demonstrate this kind of phenomenon, and that's called diffraction. And that's the spreading out of a wave after it passes through a narrow opening. So you have a wave front on this side, and it strikes a obstacle which has a small opening that's approximately the same size as the wavelength. Okay, if that occurs, then you have what happens is this perfect diffracted front, circular front, that comes out from this one point. The rest of it's blocked off. Now if you were to say squirt water at this little hole, then only water would only come through that hole, and the rest of this would have no water on it. And so this is unique to waves in that they spread out laterally away from the point of the hole or the incident where they pass through the barrier. Diffraction causes the wave to spread out evenly, when the opening is roughly equal to one wavelength. Now, if it's not equal to one wavelength, then it does not spread out in such a nice circular pattern. And this is why we can hear sounds if somebody's on the other side of around the corner of a door is open, you can still hear them because the sound waves will diffract around the obstacle and are not stopped by the obstacle. The last phenomenon I want to talk about is the phenomenon of interference. And there are two types of interference. There's constructive and destructive interference. But first, let's define interference. Interference is the reinforcement or cancellation that occurs when two or more waves collide with each other. Now remember that diffraction, reflection, and refraction were all phenomena that occurred when a wave ran into something else. Interference, on the other hand, is what happens when two waves run into each other. And so if the wave front is enlarged, that is, the crests are bigger or the troughs are bigger or both, then that's called constructive interference, and that's shown at the top. On the other hand, if the two waves negate each other such that you end up with a straight line or something much smaller than either wave by itself, then that's called destructive interference. Now, the top is an example of perfect constructive interference because the wave that results is a perfect addition of the two waves that ran into each other. And the second is an example of perfect destructive interference because there's no wave left. They both go away. And so there are obviously situations where interference occurs to a less complete degree or a greater degree.